In this unit, we're going to introduce and examine the concept of vorticity, a conserved property of fluids which is closely related to the fluid's spin, and it provides a convenient means of predicting the time evolution of flows. We'll start with the geostrophic equations, which have been developed from the rotating momentum equations under the assumptions that the flow is steady, thin and wide, rapidly rotating, and inviscid. In the horizontal directions, the geostrophic equations describe the balance between the Coriolis acceleration and the horizontal pressure gradients, and in the vertical, the flow is hydrostatic. This set of equations describe a balanced state that is time independent. That is, these equations are not able to describe the time evolving flow, which is a vitally important pursuit for forecasting significant weather events like Cyclone Winston here. In order to describe the time-dependent flows, so as to be able to predict future weather events, we actually need a new set of equations. So we begin with the geostrophic equations in x and y, and we subtract these from the total time derivatives of the flow in the x and y directions. We can then expand these out to get a pair of equations with the complete set of advection terms. The first terms we can get rid of are these two: vertical velocity times the vertical shear, or the vertical gradient of the horizontal flow. We can do this because we are assuming the vertical velocities are small, or that the Taylor-Proudman theorem is in effect. Either way, we are only interested in the horizontal velocities within this thin, wide flow. We then cross-differentiate the two equations. That is, we differentiate equation number 1 in y and equation number 2 in x. This returns a common pressure gradient term, that is, the second derivative of pressure in x and y. We can use this term to combine these two equations. The product rule is then used to expand this expression, which is then rearranged and reduced to give an equation with the total time derivative of the Coriolis parameter plus the x derivative of the v velocity minus the y derivative of the u velocity plus the horizontal divergence times the same group of terms as with the total time derivative. At this point, we define zeta as equal to dv dx minus du dy, and we make the substitution for zeta back into this previous equation, returning the total time derivative of f plus zeta plus the horizontal divergence times f plus zeta is equal to 0. This equation is called the vorticity equation.